Swayam Prabha. Digital India. Educated India.
So good morning again, welcome back, and I hope you learned something yesterday. How do you feel? Is it comfortable? Yes, sir. Yeah, and the frequency at which, of course, some of you are familiar with the corrosion problem, but otherwise the frequency at which we are modulating the lectures is okay? Level? Is that okay? Yeah, today we will do two lectures. One is, the first one is this, that is some corrosion protective solutions, which we'll see that everybody wants to change the corrosion protective solutions into green chemistries, and so we will look a little bit into that. There are so many things within that, and we will not be able to look everything, and maybe some of them we will look very briefly, some of them we will look a little bit more detailed, and irrespective of that, the important thing is that at the end of the lecture, you should get an idea about this is what is going on. I think that's all we can expect. It's not necessary that every detail you should understand or remember, but you get an idea about this is the kind of area at which the research is going on, and people are trying, different industries are trying different things, and that's the most important thing. That should be the end goal. The take-home message should be that at the end, not to get too much detail of it. And when we look at the protective solutions, what I'm going to discuss, then another lecture I'll give today is on recycling, material recycling, which is another important issue, and I will focus more on the aluminum recycling, because this is also the area which we also work with, and not only that, that's also one of the most important recycling issue today, so that's what I'll focus in that lecture. When we talk about these corrosion protective solutions, how green are they? Basically, we are discussing about putting a barrier to the metal. Barrier can be like, that's coating. If you paint the metal and you don't have any corrosion, right? Because the environment is isolated from the surface of the metal. But coating is also not easy. There are many things involved in that. And not only from the chemistry point of view, green chemistry point of view, but otherwise as well, there is a lot of things involved in that. Similarly, you can also change the environment. Like you can remove certain corrosive agents from the environment. That's also possible. And in order to do that, again, you need to think about the chemistry, whether that is contaminating the environment or not, and things like that. So that's why that green inhibitors are there. Cleaning chemistry, in order to do the coating, you also need to clean the surface. This is also important to have a green cleaning chemistry. Green, this surface treatments. Before the coating, you need to have a surface treatment. So that's also important, and then also the coatings and things like that. So all these are areas important. So as we can see that if you are covering all those, that itself is for a semester course. And so that's what we are trying to cover within 1 hour. So we just get a flavor of it, and that's all. That's the aim of this one. But before I do that, I so these are the three things, like, yesterday Lakshman was saying that we can control the corrosion in 3 ways. One is control the environment. I put the use of corrosion inhibitor. Corrosion inhibitor itself can be many ways. It is just a common term. And application of a barrier coatings, the conversion coating and painting, not conversion coating and painting and like that. And then material modification, that's alloy design, part of things, that which we will cover in the recycling issue a little bit. When you do that, you will see that. But I will also cover a little bit more on the alloy design part when we go to the last lecture, that is the PDMS, that is proactive design and control, management, that kind of things. That lecture also I will cover a little bit into the design part. So today we will take, that I will cover in that lecture, but today we will look into the first one a little bit more. But before we go to that, just let us see that where you are now. And so why the corrosion can't be completely stopped, what we understood yesterday? Sorry? Yes, it is a feasible process thermodynamically, and it is a spontaneous process, And so that way corrosion cannot be stopped. Thermodynamically, it is a favorable process. And what is meant by an electrochemical reaction? Huh? Charge transfer, right? This is what it meant. It involves a charge transfer process, right? So the electron is, there are two half reactions. One half reaction is producing the electrons, other half reaction is consuming the electron. So there is a net charge transfer in the electrochemical process. What are the half reactions in the electrochemical process, which I already mentioned now? The anodic process, right, which is producing the electrons and metal dissolution, and the cathodic process, and that is consuming the electrons and taking, and that way it is completed. What's the meaning of potential in electrochemical process, electrochemical reaction? It will determine the energy of the system, right? We can take it like that. It's determine the energy of the system. So if we are increasing the potential, of course, sign is important in the case of potential, but just I say that in general terms, if you are increasing the potential, you are supplying more energy to the system, so it's more easy to the reaction to take place. So that means that if you are changing the potential in the anodic direction, it's more, the metal is more easy to dissolve because you are supplying more energy to the metal, and that way it is easy to dissolve. And it goes in the same way in the other direction as well, right? So it's basically you are increasing the energy of the system. So that's again the thermodynamic, with the kind of things what I mentioned regarding the waterfall. Like you are increasing the height of the water means you are increasing the potential energy, and that way you get more force, right? When the water is dropping down. What's the meaning of current in the electrochemical process? The other part, right? The kinetics part, which shows that how much reaction is taking place, and that is what is determined by the current. So these two are the important thing, and it is related. And what is the equilibrium single electrode potential, which we understood yesterday? Huh? It's a reversible condition. It's a reversible condition under standard reversible condition. What is the potential of the surface potential of the metal, and that is what is we call it as a single electrode potential, right? And so this single electrode potential is the one which is listed in the electrochemical series, and I say that these are the building blocks for the electrochemical process. You can take two reactions from the electrochemical series and try to couple it together, and then you will see that which reaction will proceed and which reaction will proceed in the forward direction, which reaction will proceed in the backward direction. What is an open circuit corrosion potential of the or corrosion potential? What is the difference between the single electrode potential and open circuit corrosion potential? Which again yesterday Lakshmana was showing with different curves. What is that? Many ways we can answer that. It is a potential of the metal in a solution. Whatever corrosive solution, so if you want to steel, and you take the steel and you put it in a sodium chloride solution, if that's the environment you want to study, you connect with the electrode, whatever potential you are getting it, and that's what you call it the corrosion potential. But if you look at theoretically, this corrosion potential is the coupling of two electrochemical reactions, right? So there is two single electrode potential. One single electrode potential corresponds to the anodic reaction, one single electrode potential corresponds to cathode reaction. If you couple that together, you get a mixed potential, and this mixed potential, that's what you are measuring it as the corrosion potential, right? So the actual potential of the metal in that corrosive solution, where again the anodic current is equal to the cathodic current, anode reaction rate is equal to the cathode reaction rate. We call it as not equilibrium potential, but that's a steady state potential. It's not in equilibrium, but it's a steady state condition in that case. So that way the mixed potential theory also we explained, right? Because we are coupling two single electrode potential in the electrochemical series. Once you are coupling it to potential, you get the net potential somewhere in between, and that is what is one is polarizing the other, and that is what we call it as mixed potential, and that's what you are measuring as OCP as well, or corrosion potential, right? This is something which we have seen yesterday. I just want to little bit take that back, which what Letman mentioned, because that's important today, of when I discuss about little bit about this inhibitors and things like that. So this is what similar to that only Lakshman was showing yesterday. That is, we have, if you take a steel surface, we have the manganese sulfide inclusions, and so that's a steel surface manganese sulfide inclusion. This manganese sulfide is, we can say that's acting as cathode, right? And the steel surface is acting as anode, for example. and that is coupling together. So one of them is corresponds to the cathodic part, one of them is corresponds to the anodic part, coupled together, and then you get this I core and E core. If you are measuring it, corresponds to the steel surface, right? Right? Is that correct? Yeah, that's what you get. On the other hand, if you have a brass screw and same material you used here for the nut here, and then you have this screw is made of brass, and then you will see more corrosion on this mild steel. That's because now you have a two cathodic area. One cathodic area is this, that is on the surface of the steel, and you also have another cathodic area here, that is this screw, right? So that's what is shown here, that's the corresponds to the iron. It has a self-corrosion potential. This is for the brass, it has a self-corrosion potential coupling cathode and anode. But if you put these two together, then you come to a new E core corresponds to both together, and I core corresponds both together. That is a coupled potential and the coupled current. And you can see that brass is increasing the corrosion rate of the mild steel, right? So this is something, this is what we have seen, coupling these mixed potential together. If you have anything which is not clear, just immediately ask, okay? Don't wait till the end, not necessary to wait till the end. So that's what, if you are taking an iron and copper piece, if you are connecting, you will see that there is a current which is passing through the circuit between the anode and cathode, that is this current value here. And then you also get this voltage you can measure, and this voltage is the coupled potential of that coupled, right? So what it means the I core value, that is one is the surface area of the anode and cathode. So the higher surface area means more corrosion can occur, which also means that if you can block one of these, and that also will reduce the corrosion rate, right? Especially the cathode is an easy thing to block. Why? Because most of the time cathode exists as second phase particles like this. So the overall area of the cathode on a surface is less than the anodic area on an alloy. So because of that, it is much more easy to block cathode compared to blocking the anode. But if you block the cathode as well, because those two acids go together, you can reduce a corrosion problem. Rate of anodic and cathodic half reaction, and this is again coming to the cathode. The rate of cathodic half reaction is more important because it can drive the anode reaction more. So that comes a little bit is if you increase the area of this one, then you get more corrosion on the anode side, right? Number of cathode reaction possibility, which I want to take a little bit more today, that is, this is something which also will use for the inhibition. Cathode reaction possibility. Yesterday, Lakshman was basically, we wants to teach you the theory part, and so he was focusing mainly on the hydrogen reduction reactions. But at the end, Lakshman was also showing that the stability diagram for the water in the pour diagram, and I was showing that actually there can be more reactions, more cathode reaction, that is depending on where you are on the pour diagram and what kind of pH conditions. So it's not like one cathode reaction is possible, that is hydrogen reduction. There are many cathode reactions possible, and this is an important thing. As the number of cathode reaction possibilities in the solution increases, you also get more corrosion because it is building up the cathode side, and you get more corrosion. We'll come to that. Similarly, we can also look in the other way. That means that if you can remove the cathode reaction species from the solution, and you can also reduce the corrosion. Possibility of corrosion product film diminishing the corrosion rate. This is again Lakshman mentioned as the passivity, right? So sometimes the corrosion product film forms, and that makes the material passive, some metals, and that also will reduce the corrosion. And so that means that that's also important thing. We will see that because when we are using a passive metal, you can also make the metal to be in the passive region, and we can also use certain inhibitors for that. Galvanic coupling, I think I don't think that's that important today, but it is cathodic anode area ratio, and exchange current density is important, and all those things he mentioned, right? But I think there is also a figure coming to that. So that exchange current density which is mentioned, and I just want to focus again a little bit on that, because so this is, you can see the aluminum alloy here. So you have this iron containing intermetallic particle. This is a type of aluminum manganese iron intermetallic particles, and it's also, you see that aluminum with the silicon particles in it. Although if you take these silicon particles, you have a certain area ratio, and if you take the iron particles, certain area ratio, even if you take the same amount of silicon particle and aluminum iron particles, still you will see that the corrosion rate of this material is higher compared to that of this one. That's because although there is enough area for the silicon and iron here, but iron is a better cathode from the point of view of exchange current density. So you can drive more cathode reaction on the iron surface compared to that silicon surface. Silicon is not kind of a semiconducting. So it's not that a good electrode surface. So the reaction occurs very slowly. So exchange current density is lower, and that way here you get lower corrosion rate. And this is a typical issue in the aluminum alloy, because aluminum alloy can have iron impurity as well as silicon impurity. Sometimes what will happen is you get, after the recycling, you get more iron impurity. Sometimes you get more silicon impurity with less iron. And people see that whenever you have a less iron, still it forms similar type of particles with silicon, and but the corrosion rate is lower. Those alloys are better than iron. So having more silicon in the silicon impurity is okay compared to that of iron, exactly because of this problem, because silicon is not a good cathode compared to that of this one. So you can see that how that is important in actually when this hetero aluminum, when they are thinking about making a recycled alloy, they need to understand this. Okay, maybe I can have a little bit more silicon from the recycling process. That's okay to allow. It's not that sensitive to the corrosion, but I need to control the iron like that. Now coming to that different cathode reaction which I mentioned, which if you take this Porbet diagram, you can see that depending on where you are on this across this potential value, depending on if you are taking a metal, magnesium, you are here. If you take aluminum, somewhere maybe you are somewhere here. And if you take noble metal like gold, you are here, like that, right? The potential values. And depending on that, if you are cathodically polarizing, that means that from the potential you are coming down, you can get any of this cathode reaction can occur. So you can have the hydrogen reduction, which Leshan was focusing yesterday. You can have the water splitting. If you are coming here to this level, you can have the water splitting reaction. Similar to that, you can also have on the top part, if you took a look at it, there is 2 oxygen reactions where they use the oxygen. That's an important thing. Why that's an important thing? Most important things from the corrosion point of view. These reactions. Why that is more important from the cathodic point of view? Sorry? That's alkali is produced. That's what you are saying, right? That's coming to that. That's another thing. That is, most of the corroding systems are around the neutral pH conditions. Around this area, most of the corroding systems are. Not in the alkaline condition or acidic condition. If you take the seawater, which has a pH close to 7. Similarly, if you look at the fluids that is used in different applications, heat exchangers, you have a pH around that, close to that 7. So that means that most of the corroding solutions are around 7. The amount of hydrogen ions in the solution is significantly lower. So that means that that shouldn't be the dominating cathode reaction. So the dominating cathode reaction will be oxygen, which is dissolved. If you take water, there is some dissolved oxygen, and the dissolved oxygen in the water can use and produce these reactions. This reduction reaction, especially this reaction, is more important, and that reaction can take place around this pH value. So that is the importance of that one. So oxygen is a very, very important species in relation with the corrosion, normal corrosion issues. And that's the reason that everybody wants to remove oxygen from the system. And that means that if oxygen is removed, basically you are removing the cathode species, because hydrogen is inherently less in the neutral pH condition, and that way you can remove. So you will see that later. So oxygen is an important thing in this case. But you can also have additional cathode reactions. For example, in the carbon dioxide environment, carbon dioxide will dissolve into the water, produce a carbonic acid, like soda. That's nothing but the soda what we drink. And so that dissociate, and that can also produce this bicarbonate ions, and then you can also produce H plus after this, and that way this also can produce a cathode reaction if there is. So in the oil and gas conditions, they remove the oxygen. but still they get the corrosion problem because they are the carbon dioxide, and that will also participate in the cathode reaction. You can also have the H2S related cathode reaction. H2S is splitting into H plus and HS minus, and this H plus can reduce like what we are seeing here. So removing the oxygen doesn't mean that there is no other things. Again, it depends on the corrosive systems. It's more complex than that. But removing the oxygen in a normal condition is serve a lot of purpose. That's the reason that in the heat exchangers, in the wind turbine, there is a heat exchanger sitting. They need to use hundreds of liters of solution in that heat exchanger. They remove the oxygen from the system because then they can reduce the internal corrosion of the tubing of the heat exchanger. That can be reduced by removing the oxygen, and then in addition to that they add the inhibitor. So it is used. That's what I want to bring it, that it is used in many places, this removing the oxygen, and that way reducing the corrosion problem. So why the oxygen is this one? Because oxygen is concerned, like for example, oxygen, when you have the oxygen reduction reactions, normally we draw the cathodic curve like this. We don't the cathodic curve in a straight manner like this. We don't draw the cathodic curve like that, but we draw the cathodic curve like this. What is the reason for that? Huh? Yes, because there's a limiting current. Because in the case of oxygen reduction reaction, oxygen is there in the solution, and you are having the metal surface. Oxygen has to come to the surface for the reduction reaction to occur. So that means the diffusion through the water, this water layer is important. Diffusion takes time. The molecule has to move. It takes time. So when the reaction rate is keep increasing, as the potential is increasing, more and more oxygen has to be reduced. This oxygen has to come to the surface. It will not be able to keep the concentration what is needed. So that means that at one time you get a net depletion of oxygen on the surface, and then you cannot increase the current more than that. Even if you increase the potential, you will not change the current, and you will reach a limiting current value depending on the amount of oxygen in the solution. This is what happens. So that's why we draw the curve like that. This will not happen with hydrogen, because hydrogen is a small molecule, a small ion. Hydrogen, two things are there. One is that when hydrogen is present in the solution as ions, so that means that we don't call it as diffusion anymore. It's a migration, because the field also affects because of the charge. And it's a small thing, and that means that it can move faster. So that means that hydrogen molecules, hydrogen ions will not suffer from this limiting reaction. What is a good thing and bad thing about the limiting reaction? The good thing, bad things about limiting reaction is that means that if you have oxygen concentration higher, you can more oxygen is there to move the surface, so you get higher and higher corrosion rate as oxygen is increasing in the solution. So moving from here to here is with increasing the oxygen concentration, or you can also think that even with the same oxygen concentration, how can you increase the diffusion? How can you increase the diffusion in a film or a layer or bulk solution? Huh? Agitation. If you have stirring in the solutions, and then you can increase the flow of this one, right? You can increase the temperature. If you increase the temperature, diffusion will be faster. So all these parameters will increase the oxygen diffusion, and that way you will have more shift, right? You can see that in actual practice. This is exactly, again, if there is an oxygen in the oil and gas condition, this is a problem, because inside the oil and gas condition, when the oil and water is coming out, it has sometimes you have a laminar flow, sometimes you have a turbulent flow. Turbulent flow means you are heating the surface, and that way you are making the oxygen to reach the surface very fast. Another thing is that why this part is corroding more. When the wind turbine is in the sea water, they are not worried about the corrosion below the water. They are worried about the corrosion here. This is the place they put the heavy duty paint, because this is the place where they see the corrosion problem, because that's the area where the sea water is splashing. They call it a splash zone, and there you have the corrosion problem, because oxygen is always replenished here very easily, and you can have a higher concentration of oxygen, and you can have a higher corrosion rate. So there you can see the importance of this. This, as I mentioned, that this will not happen in the hydrogen case, because hydrogen is easily migrating. How we can also good thing about this, because again it depends upon whether it is a bad or good or bad. It depends upon whether you have an active metal or passive metal, for example. So here you can see that when you are increasing the oxygen concentration, or if you are agitating, or if you are increasing temperature because of this limiting current shift, is not good in this case, right? Take the oxygen concentration. So as the oxygen concentration is increasing, it is not good because the corrosion rate of this active metal is increasing, right? But on the other hand, you look at here, that is a passive metal, actually increasing the oxygen concentration is good. This is what Lakshman was also saying yesterday, because you need to think that a passivation is an oxidation of the surface, oxygen is an oxidizing agent, and oxygen, if there is more oxygen, you can form the oxide better, and that way having more oxygen in this case actually shift this potential to the passive region, and in this case is good. Actually this you can make use of, right? That means that if you are using a passive metal, basically when you the OCP condition you are here, you are not in the passive state, right? Is that, you agree with that? You are not in the passive state, you are here, but you need to put it in the passive state, and very easy to do that, because either you change the oxygen concentration in the solution, which might be difficult, but you add an oxidizing agent, and this is what we call it as oxidizing inhibitors. So you can add an oxidizing agent, and that way you can shift the potential to passive region, and then you can get the stability. Passive metals like stainless steel, nickel, and all these things, that's possible. So again, when we talk about the oxygen concentration, it depends upon the type of the metal, and if it is passive metal and actually having an oxidizing condition is good. With that, just background, let's look a little bit more into this control of the environmental part, that is using the corrosion inhibitors. And this is exactly what they do in many cases. That is two ways you do. One is that now you are thinking about the active metal, for example, especially in the oil and gas applications, where they use the carbon steel as the tubing. So oil and gas application is like this, that is, you have an oil well. So you will have an oil well, and the reservoir is sitting somewhere here. Reservoir is sitting somewhere here with a lot of oil, and so they put this, drill this wall, come into the reservoir like this, and so once you drill this hole, and at least this part of the well is made of metal or alloy, and once it into the well here, and then because this oil is in the pressurized state, once the drilling is over, automatically the oil will come out because the pressure in the well, that's enough. And when the oil is coming, so maybe the whole distance here can be 6 kilometers. So 6 kilometers they drill into the this oil reservoir. Oil is coming out, and when the oil is coming out, it is in contact with this metallic tubing here, and this oil containing water as well, with the CO2 and H2S, and that is causing the corrosion problem. So that means that there is not much oxygen here in this case. Actually, the oxygen is coming from, sometimes what will happen is this reservoir. So for example, initially reservoir is very solid reservoir, so it has to be fractured. The reservoir has to be fractured so that the oil will come out. This fracturing is done by some putting some acid into the well. So this acid they need to deoxygenate. Or what will happen is sometimes they add the inhibitor into the solution so that the corrosion will not be high. This inhibitor solution has to be deaerated. This is one thing. Second thing is, now the oil is coming out. For a period of time they produce oil. Then as the oil is coming out, what will happen to the pressure in the reservoir? Pressure will drop. It will reach a stage that there is no, because the self pressure in the reservoir, oil cannot come out. So what they do? They drill another well here, like this, to the reservoir, and pump water through this to the reservoir. This water will push the oil into this tubing, and this is what they call it as enhanced oil recovery. You can push water, you can push carbon dioxide into this All these things you can do, but everything is dependent upon how much it costs. The cheapest one is water, you know that, and not only water, but water coming from the sea, because some of the oil rigs are sitting in the sea, inside the sea. So because of that, the sea water is the cheapest to inject. So they inject the sea water. When you inject the sea water, you know there are two problems. One is the oxygen problem, another one is the sodium chloride problem. This they cannot avoid, but at least this they can remove it. And this is what they do to reduce the corrosion problem. So that's where this is important. That is, if you can add some kind of scavengers which can take this oxygen, and then it is a good thing. For example, people use sodium sulfate and hydrazine, which is not that much problematic for the environment, and still they use that, and that will take the oxygen and from sodium sulfate, and this forms this nitrogen and H2O, and that way the oxygen is removed from the system, and so that way they can remove it. They need to use these chemicals because normal deaeration method, like passing nitrogen on argon, will not work, because what we are talking about probably 5,000 liters of more than that of water every day. That's what we are talking about. So deaeration method will not work. They need to use such kind of chemicals for that. So if you divide into these inhibitors into the two classes, we can say that there are interface inhibitors, and then there is environmental scavengers. The one what we talk about this is the environmental scavengers. For example, removing the oxygen system, that's the environmental scavengers. But among the interface inhibitors, there are oxidizing inhibitors, which is usually for the passive metals, anodic and passive metals, where you can do the oxidation, what I mentioned like earlier, using the curve I showed, increasing the oxygen concentration. Other one is the cathodic inhibitors. Basically, the cathodic inhibitors are blocking the cathodic site, basically blocking the cathodic site. That's why I mentioned that earlier. Whenever think about the steel surface, the more important thing is the cathodic part, the manganese sulfide. Or if you are thinking about aluminum alloy, more important part is the iron containing intermetallic particles. If you can block that, automatically you blocked the anode reaction. So the cathodic inhibitors are basically something which comes and sit on the cathodic part and act as a barrier, and that way the corrosion will not occur. And this technology is available for a long time, and today when the people are trying to replace the chromium in the coatings, and people are also trying to make this into a conversion coating as well today, instead of just using as an inhibitor. I'll come to that. So that's blocking the cathodic site. But mostly major use of inhibitors in this case is for this, that is mixed inhibitors, where you have the anodic and cathodic site, both are blocked. Basically it forms an adsorbed film on the surface of the metal, and that way both are blocked, and that way the anode reaction is reduced, both anodic and cathode reaction is reduced. There are so many chemicals they use today for these mixed inhibitors, but all these are also having environmental effect because it's poisonous and things like that. And this we discussed about these environmental scavengers like hydrazine and sodium sulfate to remove this oxygen concentration. So if you take these oxidizing inhibitors, that you can use the chromates and manganate, and you can think about many other type of species that is possible, which can have enough oxidizing power. That means that if you take a stainless steel material, and if you want to use the stainless steel as a material for the heat exchanger, and you want to pass a coolant right inside, you can add a little bit of chromate that into the heat exchanger solution, and then you can raise the potential of that into the passive region, and that way it is protected interior. And this is what people were using as well. But the only thing is that chromium is banned today because of the carcinogenic effect, and the chromium is no longer allowed to use for these kind of applications. People are moving into manganate systems, for example. It's not the manganate is a very good system compared to that of chromium. Manganese is also a heavy element. It also causes problem. And so manganese is also not good, but it is only cause thing is that it's better than chromium in many applications. So in effect, what is happening is that both chromate and manganate is replaced today, and people are trying with many other organic systems which can inhibit the corrosion. That's what people are trying rather than using any of these oxidizing inhibitors. But chromate was one of the best oxidizing inhibitor from that point of view. You will see that chromate is everywhere, and it is impossible to replace chromium, but we have to replace chromium because chromium is carcinogenic. So, but in this case, basically the idea is that you raise the potential by adding these chemistries, and then you can increase, put into the passive region. But it's also important here to understand that if you add too much oxidizing chemistry, you raise the potential to here. Then you do the opposite. So, it is very, very important to control this level, and that way you can get, you can avoid that problem. Which people will control the concentration, but still they get into the problem. Why do you think that? What do you think that? Because of the design of the component. For example, in the heat exchangers, you have many like bending and things like that. So somewhere, if the solution is stagnant, and the solution stagnancy of the solution make the concentration of the chromate higher in that region, and then you raise the potential of this one into the pitting potential value, and then you get the corrosion problem there. So you expected that your concentration is you kept constant, you will not have any problem, but because of this issue and the kinks and things like that, you raise the concentration in that region, and suddenly you will see the pitting. So when you analyze, after do the failure analysis, you will see the pitting in some places, which this kind of places, and you don't understand because you think that the concentration is used is enough, but this is the reason that is happening. It happened actually in the wind turbines and things like that, and many of the these HHs have failed in that case. Cathode inhibitors are basically works with the precipitation mechanism, which I mentioned also, that is because is also used as a conversion coating. A typical example is cerium, and in the cathode inhibitors mainly we make use of this cathode reaction. Again, this oxygen based cathode reaction is an important thing there, which I am mentioning here, right? Yeah, this cathode reaction is important thing there because this cathode reaction produces OH minus ions as a byproduct, right? Right? So since OH minus ions are producing as a byproduct, we could use that thing for many things to inhibit the corrosion. When the OH minus ions are produced, what happens to the pH? Go to the alkaline condition, right? So the alkaline condition, when it goes to the alkaline condition, think that there is something there in the solution that will precipitate in the alkaline condition, right? All of you know chemistry, right? So for example, nickel will precipitate as nickel hydroxide when the pH is in the alkaline condition, like that, right? And magnesium will precipitate as magnesium hydroxide in the alkaline condition. The acidic condition is soluble, in the alkaline condition precipitate. So if you have some metal that can precipitate in the alkaline condition, that automatically precipitate here because this is a region where the cathode reaction is taking place and producing the OH minus ions. And this is what people make use of making these cathode inhibitors. It was not. I think this is also important to say. Earlier, the cathode inhibitors means cathode poison. Cathode poison is arsenic. You can add arsenic, and arsenic will come and sit on the cathode site, and that will reduce the cathode reaction. You can add bismuth, and all these will come and sit on the anode site, cathode sites, and reduce the corrosion problem. This is earlier. I did experiment with arsenic. When I think that now I will not even touch arsenic. When I was doing my master project, I wanted to charge hydrogen. And so in order to change the amount of hydrogen charging, what you do is you add arsenic as a poison. So by using the same current density, same potential value, but you can change the amount of this one, basically you are making the surface less active, like that. And the arsenic I used to do the experiment, I was not knowing that time, I used to just take it and put it like that. And even now, I don't think that any of the students will touch arsenic. And so you have to think that that poisons like arsenic and bismuth, that is what is replaced today with the cerium. Cerium is a material element that is better from the greenish point of view. Lithium is a good thing. Lithium is also, people are also now working with the lithium, so that will form the lithium based compound, because you can see that again how the Porbay diagram is useful here. If you look at the Porbay diagram like what Leshan was saying yesterday, cerium is not stable, is very stable in the alkaline condition, right? Cerium will form cerium hydroxide. So that means that then you can assume that the cerium is there in the solution. It will form the cerium hydroxide and deposit on the cathode, and that way it will reduce the corrosion problem. So you can think from that point of view. If you are designing instead of cerium, you want to find another element, you look for his Porbet diagram and see that that gives a possibility of that precipitation here, and then you can use it for this purpose. So that's why there are other elements as well, lithium and titanium, all these are also coming up. The third thing is this interface inhibitors, and interface inhibitors are naturally, all of them are organic compounds. Understandable, because organic compound is the one can easily absorb on a metal surface. What is needed for a chemical to be absorbed on the metal surface, or a molecule to be absorbed on the chemical surface? Metal surface. It should have some charge, right? So basically, you should have, we have studied in the chemistry, there is ionic bonding, there is covalent bonding, there is coordinate bonding. Coordinate bonding occurs when you have a lone pair of electrons, and this lone pair of electrons is not used for anything, and it is coming somewhere, right? It can absorb and form the bonding. That's what we call it coordinate bonding. So many of these organic compounds, especially the organic compounds, contains oxygen and nitrogen atoms, and also the sulfur atoms, because if you see the oxygen, how the electrons are filled in the different orbitals, and you can get a lone pair of electrons. There are lone pair of electrons in nitrogen and oxygen, and this lone pair of electrons can come and absorb onto the metal surface, and that way you can form an adsorbed layer. So that's the reason that organic chemistry is, especially within the organic chemistry, if you are familiar with organic chemistry, heterocyclic chemistry, heteroatoms, and heterocyclic chemistry where you have nitrogen, oxygen, and sulfur in the molecule, those things are extremely good for adsorbing to the surface and protecting and forming as a inhibitor layer. So that's the reason that all these, like imidazoline is one of the best molecule what we can see in the among the inhibitors. Another one is this benzotriazole. These two are the best inhibitor molecules ever found in this case. Then there is this another compound is quinoline, and you can have, and there are many you can have. Only thing is what you need to look for is this nitrogen or oxygen containing atoms and hetero chains, and then that can come and adsorb onto the metal surface like that. There are little bit more than that here, because it also depends upon the bulkiness of the group. That means that you think that this molecule want to come and sit on the surface. This nitrogen atom, if you want to sit on the surface, this nitrogen atom coming to the surface will be, one of them is sitting like this. If another one want to sit on the side, this part will affect that one. So you need to think that this molecule is sitting, and that molecule is not allowing the other one to sit because of this part of the molecule and this part of the molecule. So what I want to say is the bulkiness of the molecule and how the molecule is also an important thing in addition to this. But heteroatom is one of the key things, and that increases the chance for. So when you look at the inhibitor efficiency, you know how to calculate. That's very easy. This thing that is basically you do the I core with inhibitor and without inhibitor and take the ratio, then you get the inhibitor efficiency from that. But some important aspects related to the inhibitors are where it preferentially adsorbed. This is an important thing. Why that is? Because basically we are talking about the metal surface. It's not the metal surface always. Take the example, like you have the mild steel, again in the oil and gas condition, and you have the corrosion is occurring. You want to avoid the corrosion. Can corrosion be completely stopped? No, right? That's what we start from the beginning. So corrosion is completely stopped means only thing is corrosion can be reduced by adding the inhibitor. So still some corrosion is taking place. This corrosion will create either the iron oxide corrosion product or iron carbonate scale. So initially you have the pure metal surface, no problem, inhibitor is absorbed into the metal surface, and you have the corrosion is reduced. Now the little bit of corrosion is occurring, slowly you are forming the iron oxide and iron carbonate compound. So this scale will be there a little bit on the surface. Think that now the absorption capability of those molecules are better on the iron carbonate scale or the iron oxide scale compared to that of metal surface, where it will go and adsorb. On the iron carbonate scale. Is adsorption to the iron carbonate scale is good for corrosion? No, because we want the inhibitor to be absorbed on the metal surface, not on the scale surface, right? So this is the thing. That's what I meant by this is where it is preferentially absorbed on the scale or on the metal surface. That's an important thing. What kind of corrosion needs to be protected? This is there. Some inhibitors are good for protecting the uniform corrosion. Other inhibitors are good for protecting the localized corrosion. This is also important. How much quantity is needed? Because everybody, when they want to use inhibitor, they want to use as much low quantity as possible because of the cost. So how much inhibitor is needed? If you have an efficient inhibitor, but you say that you want to use 5000 ppm, nobody will use it. Is some other inhibitor which can work with 100 ppm, and that's much better because of the amount what they want to use. Injection frequency is also an important thing. That is, if once you add the inhibitor, how long it will sustain? After some time, the inhibitor will be going. Part of it will be absorbed into the scale, which is not useful, and things like that. And so again and again, you have to inject it. And how frequently you have to inject it? That again comes back to similar to that. This one is how much quantity is needed and things like that. So all these parameters are important. And when we are looking for making a green inhibitor as well, it's not that it is just you can take and find the efficiency value, but in addition to that, all these parameters are important to look at it. So if you look at a commercial inhibitor which is used, for example, in the oil and gas conditions, you can see that it's not just one molecule here. There are so many things here. For example, here you can see that there is ethylene glycol in this, and there are this kind of amine product. This amine is probably the inhibitor molecule in this case, and there are few other things. And then this maleic acid they added because this is to avoid the calcium carbonate formation, because there is calcium in the well, and that can form the calcium carbonate scale, and to avoid that. So that means that all these mixtures together, and that's what is coming as inhibitor. So it's not just one molecule. Maybe one or two molecules in this case is inhibitor, but all other things are included for many other purpose to help the inhibitor or help the inhibition. And so now people are trying to make this. They want to go from these molecules like imidazoline and things like that into green inhibitor molecules. And why the green inhibitor molecules are possible? And there is a good chance that we will be able to find the green inhibitors, because any natural extract you take, most of the natural products are having the heterocyclic heteroatoms or heterocyclic chain within these organic molecules. For example, this is a riboflavin. This is in the carrot, for example, and this one is in the, from carrot, it is in the garlic. And so if you look at here, it is written aloin, for example. This aloin is there in this aloe vera plant, for example. And so any of these natural species you take, and if you take the extract, it's not just one molecule, but there are many molecules, but you will see that all those molecules have these heteroatoms. So there's a good chance that all of them can work as a inhibitor. But it's a difficult task, right? A difficult task is to find which one is good, because there are so many possibilities. When you have so many possibilities, that also makes it difficult to find which one is good from the inhibition point of view. Little bit I show you that what we do in this. So for example, we were trying to this aloe vera extract as the a corrosion inhibitor, and we find that within the aloe vera extract there are many molecules, but there is a molecule called aloin, which is shown here. This aloin is the one which is making the key molecules for the inhibition. Because we also synthesized aloin, we bought aloin, and along with the aloin extract, and we tried, because we had an indication that among the different molecules in the aloe vera, aloin is the one which is probably best acting. All other things are waste, probably. So that's the reason that we took aloin, and that way we were trying to find the inhibition effects. We found the inhibition effects. You can see that it comes back to the composition of the inhibitor, what I showed earlier. It's not good enough. For example, aloe vera with 4000 ppm gets 10% efficiency. It's not at all good. What oil and gas company is looking for, at least 90% efficiency. This is what people are looking for. We also tried many other things, because honey and things like that. And why we are trying all these? And it's not like we are trying it just like that, wild card. It's not like that. It's just, there is a theory behind it. I'll come to that. There's a theory behind why we are trying all these. And then we can see that it's not good. But you can see that this aloe vera together with ethylene glycol is working. it is giving around close to 90% efficiency. That means that ethylene glycol is helping the aloe vera molecules in the aloe vera to absorb onto the metal surface, and that way it is increasing its efficiency. Like the composition of the inhibitor, whatever the commercial inhibitor, what I showed you. Why the ethylene glycol is affecting? Still we are not clear. There are many things what we think, because the ethylene glycol can little bit make the surface much more wettable. Maybe that's the reason that is making the aloe vera molecule, this alloy molecule to absorb. So like putting a soap into the solution, and maybe it is increasing the wettability, but still we are not clear how it is affecting. But clearly you can see that there is this ethylene glycol which is influencing. Then we asked the big inhibitor manufacturers like Schlumberger, they also add ethylene glycol into many of their systems. Why do you add? What is the science behind it? They are also not clear. They know that it works, but they are also not clear that why it is working like this. So there is a lot of things which we need to in that. But you can see that aloe vera is one of the chemical that works. This is giving an example. I can go into many molecules, but I just to show you that how we are doing. I mentioned that this is a very difficult thing to do it, because there are so many extracts, right? Like think about like the whole spices what we use. Everything that you can extract something from that, and you will see this kind of molecule in this. So how do we do this? And everything, if you are trying to do the experiment, my students, if they are trying to do the experiment, most of this experiment, we do it for 60 hours, 80 hours, and things like that, 4 days, and things like that, we do. And this is a linear polarization measurement what we are doing, and then how we can do it. So we do the molecular modeling. And molecular modeling, you can screen the molecules what is better. So what we do is that basically we are asking this question. This is a steel surface. You know steel, you take the iron. Iron surface has a crystal structure. So that's crystal structure only what you see here. So iron crystal structure on the surface. So you take the iron, and this molecule is coming to the surface and is absorbing onto the metal surface. What is the energy of absorption? This we can calculate by using this molecular modeling programs. We can calculate what is absorption energy of this molecule. Not only that you can do, because you can see that in this case, if you take this molecule like this one, there's an oxygen here, so it can absorb like this. There is 3 oxygen here, so that means that it can also absorb that way. That also we can do. We can, in the program, we can say that how the molecule is approaching. Molecule is approaching, if the molecule is like this, it is approaching like this or approaching like this, and all these things we can specify in the program. And that way, which atom we want to attach to the surface, and that way we can calculate this absorption energy. So that absorption energy gives us a little bit of an idea about which molecule probably can work from the experimental point of view. How we do that? For example, we also take water. So you can see that water has OH group, right? So we absorb water and find out what is absorption energy. So for example, in this case, absorption energy for water is -31. Then we take MEG, for example, and what is absorption energy? Absorption energy for MEG is -50. So which one is better? What we learned yesterday, more negative free energy means monoethylene glycol is better. So that's what it shows. That is words like that, probably that's the reason that monoethylene glycol is working when they add into the inhibitor. Then we take this alloying fragment and then we calculate. It is -92. That's much better than all these for the absorption. Then we take the carbohydrates fragment of the alloying. That means, as I mentioned, that we can align in different ways. And you can see that again it is much better than this. But it shows that if these 3 together, it shows that it shows this alloying molecule is absorbing much better than water molecules, whatever way you put it, like that. And it doesn't mean that the same, if you do the experiment, exactly it match. But it gives us a way of screening it, and understanding is much better. So I have many results like this with different molecules, but I'm not going to showing everything, but you understood the approach, right? So that way we screen these molecules, and that way we can understand that which molecule might work, and then we do that experiment. Here we did this absorption ion. I have another table where we also do the absorption on iron carbonate. So we also do the same molecule. We think that we look into that, how it absorbs the iron carbonate. Why that is important? Which I mentioned earlier, the scale. Iron carbonate is the scale. So if the energy of absorption to the scale is better than this, then there is a chance that once the scale starts forming, this molecule will be lost because it will be absorbed with iron carbonate or iron oxide. So we also do absorption energy calculation for the iron carbonate scale, and this is a really powerful tool, and it helps a lot of especially for the green inhibitor to screen the different molecules. So that's what is shown here. I told that is aloe vera with MEG as an example. It is giving a good inhibition efficiency with a higher RP value. That's what also you see with this impedance, which we didn't discuss. Impedance is much more, some of you know, but it's much more complex electrochemistry, and that way you see. But still you can see that this is not good as imidazoline. Imidazoline is something like a wonder molecule which has an efficiency of probably 96% efficiency. It will not go to that level. It is even with, you need to remember that imidazoline without MEG, without monoethylene glycol, gives 93% efficiency. Imidazoline. Huh? Sorry? In water, in sodium chloride. In sodium chloride, it gives 90% efficiency. It will not come to that level. Even with the MEG, it comes only to the 88% this inhibition level. But there is, when we are driving as a green inhibitor, it's important, right? Because still it is green, like that. Now we are trying with, there was a problem we found with aloe vera. The problem with aloe vera is that it gives 88% inhibition, but now we can see another problem. We can also see that inhibitor efficiency drop very much after 4 days. So 4 days it works. After about 4 days, inhibitor efficiency decreases very much with in the aloe vera. That means that you need to inject it again to bring it back into the level with the aloe vera. And that's also not good, because then you need the injection frequency has to be higher. That's the reason that now we also try with another molecule, which is the black tea extract, and which also contains many of these molecules like theanine, and so this catechins. There are many molecules also in this one. Caffeine as well, we thought that caffeine is a very good molecule for inhibition because of nitrogen atoms, but we found that caffeine is worst. It's not good from the inhibition point of view, but this one is probably better. But black tea is again working, like you can see that different levels of black tea compared to the reference. This is RP value. So RP value increases means corrosion is decreasing. There is resistance polarization resistance from the linear polarization curve. So it is increasing means corrosion is decreasing. So you can see that again this is giving a good inhibition. Is it good as this imidazoline? No. Probably it gives a 60 to 70% inhibition it gives. But one good thing we found with this black tea is that inhibition is keep on going up. Even after we did the experiment for 30 days, and even after 30 days, it is exactly maintaining in that level, and it has increased more than this, but it is remaining at that level. It's never coming down. So that means that injection frequency point of view, it is working very well compared to that of this aloe vera extract, and that way it's better. But again, you can see that there is lot to go in all these, but it gives you a kind of a flavor, right? And these people did a good survey related to the different types of inhibitor used. So you can see that there are many things here they listed for the steel and different material, different types of plant extract. I don't know everything is tested or not, or they just think that it will work. And a molecular modeling point of view or anything is tested or not, I don't know. But it gives a kind of a good listing of number of things that can be used as this one. Yeah. Yes, exactly. Everything is in sodium chloride solution. Not only sodium chloride solution, since we are working with for the oil and gas and carbon capture related things, everything is in the CO2 condition, fully saturated with CO2. So there's no oxygen. So basically we are studying this for the But that doesn't mean that it will not work for other things. But we haven't tried. Since our target is for these CCS applications, so that's the reason that we are trying with saturated with the carbon dioxide. So we take the sodium chloride solution, we purge that with nitrogen overnight to remove the oxygen fully. Then 4 hours we purge it with carbon dioxide, so that solution will be saturated with the carbon dioxide. We measure the oxygen concentration to make sure that oxygen is very, very, very low. And then we do put the specimen, and then we start the experiment adding the inhibitor to that. Sorry? Inhibitor will be mixed in the solution. Inhibitor will be mixed in the solution, and it will be absorbed onto the metal surface, right, in this case, yeah. Yeah, yeah. Yes, because your case is concerned, your medium is concrete, and the diffusion is very, very slow there. And that's the reason, right? So that's the reason that it also depends upon the diffusion through the porous layer.